All right, so I guess welcome to the first. I mean, it's called Jamaica. I mean, let's just call it Jamaica AI Association for now.
All right.
Meeting. So for today's meeting, we're basically gonna explore um a theory developed by my AI researcher in Jamaica, um, called SuperSymmetric neural networks. I guess I'll let him, I guess, introduce himself and then talk a little about, you know, what his theory is all about, and then we can ask some more questions from there. So over to you, Bennett, if you hear me. Bennett, you can hear me?
Sorry, from my perspective, the video
Oh,
just
yeah, it seems
the
your
connection
connection.
just fell. It just resumed now.
Yeah, it seemed like I don't know if it's the internet's a bit choppy. Um, are you experiencing the same thing, Dimitri? Like his video feed seems a bit choppy.
Yeah, man, I see it kind of look choppy, but if video not important, just turn off a video. Maybe add a bit
Yeah,
more data, data so
yeah. Try turning off the videos so you can just speak.
the more data can focus your audio.
All right, so you can hear us now properly.
I'm hearing.
Okay, yeah. I was just saying, basically, just I guess give us short introduction of yourself, and then from there you can give a brief explanation of your supersymmetric neural networks. What are they? Kind of how you came about this theory, and I guess from there we can delve more into the details.
Yeah, man, if I want to use the diagram, the man such and such, I can use them too.
Yeah. So I guess if you want to share your screen, or if anything, if you want, I could share because I have your thing there up on Google.
Yes, perhaps you should share
Okay.
because
Yeah.
I'm now on my phone.
Yeah. I'll do that then. I'll do that. Cool. Um,
Maybe share the little paper I had.
yeah. So which one do you want
So
me
you could
to?
perhaps
Are you seeing my screen now?
you
Yeah.
could
Which
have
one do you want to share
yes,
first?
perfect.
Is this fine?
Perhaps you could have
Mm-hmm.
two things open.
Okay.
One thing, the item written by Porter from Queensland, and also my paper that I had. So if you scroll up a bit, or I'm not sure,
Mm-hmm.
scroll up or
Oh,
down.
this one.
Is it up? Maybe down.
Link. Oh, down.
No, your screen is not moving. Okay.
Are you
Scroll
seeing?
down, please, a bit more. I'm seeing something now. You're scrolling all the way. Well, not all
All the
the
way
way
down
down, but no,
here.
hold on. There.
Mm-hmm.
No, you just passed where it said paper.
Oh, so this one.
No, no. Up. Not quite. There's a
Oh,
section called paper there.
oh, this one,
Up right there,
or
open
or
review.
this.
Yeah.
Oh, this. Okay.
Yeah. The reason it is called thought curvature
Mm-hmm.
is because it involves curvatures. And also, really, I was trying to follow up from something called the thought vectors. You know thought vectors?
No, can you explain what you mean by that? I mean,
Not me,
for
not my
audience in general,
thought
or
vectors
whoever is
involve.
listening. Mm-hmm.
Yes, the thought vectors involve. I'm not a
Mm-hmm.
thought vectors expert, but they
Okay.
involve attributing weight to words, and how these weights relate helps to generate meaning, overall meaning in language. And so it is used for things like language translation and so on.
Okay.
And it was put forward. was pioneered by, rather than put forward, pioneered by Geoffrey Hinton, who co-won the Turing Award with Benja and Jan LeCun for their work in artificial intelligence. I wanted to have a similar alternate name, so I thought of thought curvature.
Okay.
A name
So
I
I
could have.
can show how I move from thought vectors to thought curvature. Yeah, like what be additional stuff, the thought curvature. Or it's just like a similar name I choose. Just because.
Just a similar name I chose,
Okay.
but
Okay.
I can show, I could show something like that. How one could move from thought vectors to thought curvatures. Hold on, could we go to the Wikipedia
Okay.
page? Sorry, not the Wikipedia page. There's a wiki page on the GitHub.
All right.
I
This one.
think. Did I have it there? Yeah. I think I was explaining this to Stone recently. If you compare, if you zoom in a bit. Oh, I can zoom. Okay. If you compare manifold learning there to to my method, which is super manifold, which involves super manifold learning. That's also another way to establish a supersymmetric NN. Is to
Before
go
you before you
by looking at
continue,
supermanifolds.
before you continue, sorry to cut you, but for the purposes of our audience, maybe you could explain what you mean by manifold learning in a simple way.
Okay, perhaps we could go back to the page, Wikipedia page again.
The Wikipedia, this one or this?
Sorry, the GitHub page, sorry.
Okay.
And we scroll down there. Yeah, stop there. That big image there.
All right,
It's a
cool.
part of the paper, but
Mm-hmm.
it's easy to isolate. Essentially, lots of things are just numbers.
Mm-hmm.
Even in physics, we have theories that all things are just simply numbers. So, for example, humans are just a bunch of numbers.
Mm-hmm.
And in the operations that act on our atoms to form molecules and so on are themselves more numbers. So in AI, in the history of AI or machine
Mm-hmm.
learning in the past, we try to use some particular sets of numbers to do certain things. And that didn't work so well. It led to an AI winter, as Marvin Minsky in his books would allude to, show the limitations of things like the perceptron. Perceptron essentially did learning through simple numbers and simple
Mm-hmm.
operations on those numbers. So that Zn, or what you see there, signifies integers being used to try to do machine learning. So think of everything in existence, or at least for this purpose, all the things that happen in AI as numbers and operations on those numbers. So numbers, for example, like numbers in a matrix
Mm-hmm.
representing some input space. And
Bef-
operation on those numbers, like
mm-hmm.
matrix operations, like matrix multiplications and so on.
Mm-hmm.
So
Before you continue
what
though,
was the
you
initial question?
mentioned, yeah, before you continue,
Move from, yes,
are you hearing me?
I'm hearing.
Yeah, I was saying before you continue, you mentioned that there were certain things that the perception was not good at. I mean, for the purposes of our audience, could you maybe explain or give an example of what the perception or why it wasn't so good at whatever it wasn't good at?
Of course. Let me
Mm-hmm.
recall. Hmm.
Um,
So the perceptron was good at recognizing simple things,
yeah.
but it failed for more complicated tasks.
Mm-hmm.
So a simple task could be recognizing a simple shape,
Mm-hmm.
but more complicated tasks involve recognizing things like pictures of cats, or just isolating those things,
Mm-hmm.
differentiating between pictures of cats and dogs. So simpler tasks it was good at, but for more complicated tasks involving hierarchies of data in the input space,
Mm-hmm.
the perceptron failed spectacularly at that. It didn't even fail per se. It's just that it didn't have the capacity
Mm-hmm.
to approximate those tasks. And as we went through, we used better numbers. So we started to use things like convolutions,
Mm-hmm.
marked there by the asterisk there in item 2.
Yeah.
Numbers involving real numbers, the Rn there signifies real numbers. The asterisk there signifying a convolution is a convolution operator between those reals or orders of matrices.
Mm-hmm.
So when these machine learning models work, when they learn a solution space or when they learn a solution, we know the solution to look like something like y hat, which is some derivative, some
Mm-hmm.
operation, some number. Remember, all machine learning is just a bunch of numbers and
Mm-hmm.
operations on those numbers. If we boil it down, it can be boiled down like that. So we started to use more more sophisticated numbers and also more complicated operations because of the numbers we're using. So different numbers or different classes of numbers have different types of operations we can do on them. And also with more sophisticated numbers, we can represent more of the input space. So for example, in the older days with the perceptron and so on, or the numbers that were used, something like integers, you can't really capture much nuance there. You can capture nuances, for example, pixel space that you want to learn and other nuances you will miss that real
Mm-hmm.
numbers would capture,
Yeah.
at least at a better rate, more efficiently and more robustly. You capture more of the input space with reals compared to things like looking like integers in the past. So on top of reals, we started to use things like convolutions as we see there. So the
Mm.
solution space that is learned is what looks like manifolds. So for example, in the older days, what did this solution space look like? Maybe hmm, when you have when you're learning the solution space, what what does a hyperplane look like? What do you learn? How do you separate the inputs? For example, if you're grouping things,
Mm-hmm.
what did those early spaces look like? In the early days, you didn't have hyperplanes yet, but with real numbered convolution system, you have hyperplanes, and that is where things like manifolds come in. That's the shape of your solution space as one explanation. And the better numbers we use, the better our solution space represented our input space. The more useful the models became. So that is what the manifolds are just
Mm-hmm.
shapes of your solution region.
All right. All right. Yeah,
So
makes
all of
sense.
the machine learning can be boiled down to that, to just numbers and operations on those numbers, which are themselves numbers essentially.
Mm-hmm. All right, so
So the
which
next,
part? Hold on, now. Which part reach again? After that, we does some manifolds. So we can get back to that. We get it to know manifolds are shaped by a solution space.
Mm-hmm.
Yeah. So you can just visualize, let's say three dimensional, but more than three dimensional space. So just have to visualize that me just assist the manifold is the shape or the space. I can use more complicated numbers. So
Yes.
yeah. So instead of use integers or simplest set of numbers, not really simplest, but yeah, either use more complex numbers.
Like reals. And literally, complex valid neural networks are another thing seen in item 3.
Yeah.
You start to use, complex numbers with the imaginary and the real parts.
Yeah.
With the imaginary section, you get to learn more of input space. In physics,
So
yes.
is this something that has been implemented with complex valid artificial neural networks,
Of
or is this
course.
more a theory? Okay.
No, it has been look at the reference there, 31.
Okay.
All of the things there point to some implementation somewhere or a
All
certain
right.
paper. All of these things are, with the exception of my model, because it's very hard. I don't have all the information yet. My
Yeah.
picture is not complete. That's the only thing that wouldn't be implemented yet, the supersymmetric ANN. But item 3, we have complex body neural networks. And that's what is the shape there? Sectors. So for each solution group that you're learning, your solution space looks like sectors. And for item 4 there, what sectors look like?
Could you give an example or?
Sectors of a circle, right?
Think of it as yet another shape. Just another shape. And these shapes involve mathematical operations.
Yeah.
Just another bunch of numbers and operations on them. At reference 31 would have an example there of a complex value net.
Oh, well, try clicking on it. Oh, reference 31. Let me see if I can find it.
You would have to go to the paper. My paper.
Oh,
Anyway,
I see.
because that's a snippet from the paper.
Yeah.
Let's go all the way to the lower end.
Is it 31? Not seeing 31. Do you remember the name of the paper? Can you hear me?
Yes, I'm hearing you, but I'm asking if you're not seeing the reference.
No, I'm not seeing the reference. It stops at 24. I don't see 31.
All right. If this version is a later version of the paper, I think.
Oh, I see.
Well, hold on. If you scroll up, you may find a similar region where I went through those solution geometries in the same paper. Let me
This one,
see.
this
Look
paper?
there, item. Yeah, that section here. I went through the same thing. The reference number may have changed.
Oh,
Item.
reference 7. Okay.
Yes, that's a later version of the paper.
So it's this one.
The 7 there, yes. My apologies there.
Complex valid neural networks.
You can actually find many papers on arXiv as well, and also several implementations on GitHub of complex value networks.
So have they found to be better than regular neural networks with real numbers?
They have been found to, yes, they have been found to be better than the state of the art real value networks.
In what sort of tasks? Image classification, object detection?
Yes.
NLP?
The standard MNIST tasks, I think.
Oh, MNIST, okay.
Probably because it's a young thing that I come with this on the basic stuff. So
it should be image.
Yeah.
But I mean, I know MNIST to be a very simple,
Yeah, but
task. I don't know
you
if
would
it's
make a difficult implementation when I just testing it for the first time, right? You try to make it simple. And you can still test it if it perform better on MNIST.
Of course.
True, but I mean, I would think they would, attempt to test it on a more complex data set to really.
I think it perhaps it would have been tested, but
Mhm.
I'm not aware of all the tests it has been done on.
But do you know of it being used in practice right now, like any complex valid artificial neural networks? Like,
I'm not sure, but I
oh,
think it
okay.
is. I think it's in some places,
Mm.
but I'm not sure. But there has been work, or there have been works following from complex valid networks.
Okay.
You can just type GitHub in the search bar to get some code. And we see the gradation of data representation capacity
Mm-hmm.
as we use more and more sophisticated numbers.
So I get the basic idea I'm getting from here is that with complex valid numbers,
It will have
I guess
both
the
real and imaginary parts.
representational power of the neural network will increase. Is that what
Yes,
you're saying?
we can
Yes.
create further detail. That's what I'm getting.
So you
So
can represent more functions and stuff like that.
you can get aware that.
So continuing from complex valid, because I mean I understand complex numbers. What's the next step from there? I think
I think, I
point
think, that-
four
so
is
I think it's
saying, yeah, point four. Can you, I guess,
So instead of just
yeah,
using complex numbers, you would venture to use convolutions with those complex numbers.
I see.
So not only do you use complex numbers,
I
but you would
see.
start to use convolution. So
Okay.
convolutional complex neural networks,
Complex valid. Okay.
which are a thing. They exist. So I think I had a reference there. Well, that
Oh, I
reference
see.
is old, but in the
Oh,
paper I would have a reference to an implementation of that, not by myself, but
mm-hmm.
by several other researchers. You'll be able to find that implementation there.
okay. Yeah, I get that. So I move on to part
Okay.
five because I'm
So I
seeing how it
mean, here
work
it's
on.
saying it may have good weights that lie in the chi distribution bound, Rayleigh space per class. I mean, can you probably explain in simpler terms what that part is saying?
We're looking at item 4.
Yeah, item 4.
We know what a distribution is.
Yeah.
That distribution is just another type of distribution.
Okay. And what do you mean by Rayleigh space per class?
So look at the item before. When you learn a solution space, or when you learn a solution, which are just a set of numbers that the model has turned out based on some input space,
Mm-hmm.
the resulting collection of numbers that you learn form a space. And when you use convolution neural networks, and you
Mm-hmm.
convolve on those complex numbers, you end up with a Rayleigh space. The
Okay.
reference would have in machine learning.
Really. Mm.
So there's a
Super
reference there.
symmetric.
Well, not that reference, you would have to go to the paper again.
Okay. Where's this paper?
Don't
So
know
it's
what option was that.
point 4.
No, you have to go back up.
So it's 8. So this one.
Deep complex networks. I think that's the right one.
Okay. All right, so what do we have here? Looking to see if there is a maybe an image or something. But let me look at the abstract.
Yes, it helps look at the abstract and also the conclusion sometimes. And then dig into the rest of the paper.
You're searching for relay space, right? Relay space. So I just Control F.
Yeah, really. Ah, here it is. Oh, so it says, so it seems it's a tri-distributed with 2 degrees of freedom. So let me, I guess, look for that Rayleigh distribution. Ah, okay. So Rayleigh distribution is a continuous probability distribution for non-negative valued random variables. This is essentially a tri-distribution with 2 degrees of freedom. Okay. I mean, I guess we're not gonna go too much into the math of all this, but I mean, I get the gist. Going down.
More numbers
Mm-hmm.
and more, I would say, in some cases, more sophisticated operations on those numbers. We can learn more of the input space.
So it says here that it may guarantee more variation of the weight space. I kind of get where you're going with that. But here it's saying it's by learning phase space representations and by extension, strengthen these representations via convolutional residual blocks.
Yeah, so what, okay.
Yeah.
What
So
does
maybe
phase space representation mean?
Yeah.
When in the typical machine learning sense, we normally learn magnitude. But with complex convolutions, we can learn something else. We can learn some information about the phase space. Phase space is just another collection of information about the input space. So so beyond magnitude, we learn phase.
Could you give an example?
Okay.
Of what we mean, what phase would look like? I mean, I understand what magnitude is, but phase, could you give an example?
The best way I can do that is to go to look on one of the references.
Oh, okay. So the same paper that we're just looking at?
Explain it far better than I do. I'm not hearing.
Yeah, the same paper, this paper that we're looking at, or whatever?
I think so. Maybe type Control F for phase, just for phase.
Phase, okay.
You can also go to Google and type magnitude and phase and see what comes up.
It says your frequency response, quantitative measure of output spectrum of a system or device in response to a stimulus, is a measure of magnitude and phase. All right, I'm gonna right click on this, see what they mean by phase. In physics and mathematics, a phase of a periodic function f, some real variable t, is an angle representing the number of periods spanned by that variable. Okay. Oh, okay.
So it looks like in nature, there's more information than magnitude embedded in what nature has to offer.
Okay. Okay, I think I get it now, because when you're saying phase, waves being in phase, this definitely comes from physics.
So that means you capture more than the magnitude of
Yeah.
the input space. So what this is saying about machine learning in general is that as we borrow more from physics,
Yeah.
we can extract more about the input space.
Mm-hmm.
So we don't just stop at one set of characteristics like magnitude,
Mm-hmm.
but we also grab more
More
characteristics
information,
like phase.
which as you said, leads to better hypothesis. I guess.
Yes.
All right. So I guess the last point here, number 5, which is your original work. I
Yes.
guess, yeah.
This is
Let's
the part that I wanted to get. Yeah. So supersymmetric. We're getting to supersymmetric.
Before we continue, guys, the Zoom meeting time is running out. So
Okay.
I'm
And
gonna
the
end this
first
meeting
record.
and then you just click back on the link. All right.
Oh, okay.
All right.
This shows an overall layout. So we look at the bottom left section.
Mm-hmm.
First of all, what is this graph indicating? So we're looking at machine learning in terms of representation power, because the more of that we have, the more sensible the model gets, the more useful things it can do. And the less of that we have, the worse the model tends to be, or the older the model is older the right word, the more obsolete the model tends to be.
Yeah. Less effective. Okay.
So on the horizontal axis, we have symmetry group structure, connective degree, or preservation depth. And on the vertical axis, we have representation power.
Yeah.
So we see something called orthogonal there, not connected, gradient descent incompatible. Normally, if you do an operation on, like say, a matrix,
Mm-hmm.
and you can't get it to be invertible, for example,
Yeah.
you can't get any solution. You can't do gradient descent on that
Mm-hmm.
matrix structure. So that is why orthogonal structures are gradient descent incompatible,
I see.
because they're not connected in that respect. And following from that, we have SON based models. For example, there's a paper that implements special orthogonal models. Right in the section below, you see it. So right after this graph, you're going to see, if you can scroll on a bit, Matthew,
Yeah.
scroll till you see the description, the part on the yes. So all of these are implemented, well, with the exception of the supersymmetric alien, which is not yet done.
So I think
So
we're
the
just
reference
at
is there.
special orthogonal. I don't think did you finish explaining that one? Special orthogonal.
Now I'll just point you to some references.
Oh, okay.
What reference was that? For the
Which one?
special,
Yeah,
I think 3 and 4.
I'm looking at this paragraph because I mean you started explaining, the graph with, representational power versus symmetry group structure. And I guess I wanted to ask you, what exactly do you mean by symmetry group structure?
No, I didn't hear that.
Yeah, I was asking you, what do you mean by symmetry group structure, connectivity degree? What does that mean?
So all those things you see here, ON, SON, SUN, they're all members of some symmetry group. Connectivity means if you do an operation on one structure, how connected is it to its translation? So if I do, say I have some matrix M, and I do some operation on matrix M yielding M prime, how connected is M prime to M? Can we revert M prime in a reasonable way to derive M? So things like that means if we don't have that type of connection between those translations and the origin, we can't do, we know how gradient descent works. Backpropagation, we have to, and backpropagation normally involves chain rules and so on.
Yeah.
If we can't form a chain, we can't connect, it's worthless to us.
Yeah.
So that is why things like orthogonal group-based algorithms can't do gradient descent. But as we move up to things like special orthogonal groups, it has that characteristic of being connected, therefore gradient descent compatible. So if you go back up to the graph there, please.
Yeah.
Matthew, can you scroll up to the graph for a moment? The same place.
Are you seeing it?
Well, I'm seeing part of, yes, I'm seeing it now.
Okay.
So with SON, look at the characteristics here. We have gradient, and this normally concerns normal space-time. So in physics, they use
Yeah, I think you chipped out. Are you hearing us? Ben, are you hearing us?
Yes, I'm hearing now.
Yeah, I think you kind of chipped out a bit. You were
Are you
explaining
hearing?
normal. Yeah, I'm hearing you now. I think you were explaining normal space-time. Are you hearing?
Bennet, Stone.
Yeah, you can hear me, Dimitri?
Yeah, I'm here.
Benny, you can hear me?
Sorry, I'm hearing you now. My Wi-Fi completely,
Oh,
the
okay.
connection itself fell.
Oh, I see. Yeah, you were explaining normal space-time. Yeah, what were you saying about that?
Yeah, so I'm trying to draw a corollary between the symmetry groups being used in physics versus how they're using machine learning.
Yeah.
So in physics, I don't know everything about physics, but this special orthogonal group here is using machine learning. And if you look at the characteristics here, and compare those to the special unitary group above, we see some more characteristics coming out. We see orthogonality, complexity, or rather use of complex numbers, and symplectic preservation. All these things mean, how to explain it simply? you get more representation for
Mm-hmm.
you go to special unitary matrix-based machine learning. Due to these things that hold true in the case of special unitary matrices and the operations, you get things like orthogonality and symplectic preservation. I don't quite recall what symplectic preservation incorporates now,
Yeah.
but I remember that you get to do more things in the input space. You get to preserve more things when you when you do learning compared to the prior symmetric group. And when you go to unitary group, unitary matrix based models, you get more of the unitary capacity. So special unitary group was a special case of unitary space, but the unitary group is a full, is a delimited space or delimited version of the unitary space. And all of this is seen in the paper's reference. So one paper, for example, showed that using, when you have access to the full unitary space, this yields more representation for, and you do better in state of the art, sorry, better than the state of the art in
Mm-hmm.
particular tasks. Think of it as having more operation to apply to your input space. At the end
Okay.
of the day, all of these are essentially numbers, operations on those numbers, which are numbers themselves. And the more useful your algorithm is at extracting or representing the input space, extracting information from the input space or representing it, better results you yield. Well, that has been the trend from
Yeah.
experiment.
So, all right. So this last one here, SUM bar in.
Yeah, so that is not my
Mm-hmm.
notation. If you go to physics, I think I have a reference at the bottom. Physics, if you go to symmetry, okay, scroll down a bit to the references, please. All the way to no, the references. Hold on, stop there. Look at item 5, please. Maybe in 23. Please scroll to. Yes, that's it. Symmetry groups. No, 23. Yes, yes, yes. Algebra, that's right. Supersymmetry algebra on Wikipedia, I think. You'll see that it's a standard thing used from physics. It's not there. Look if you see SUMN somewhere there. Same place, same place, same page. You don't see it there? No, you should see it in the same page, supersymmetry group page.
The top page. So you're looking for SUNN, so Control F.
Something like that, yes.
Supersymmetry neural networks.
Or you can Google it as well. SUMN.
Okay.
But it's not my notation. No, no. Yes, that's it.
Uh,
Bar in physics. No, that's a special unitary group. That wouldn't be it. Unless the page change. No, it should be on that first page that we went to, SuperSymmetry group. No, not that one. Yes, hold on. Is there a SuperSymmetry group page that is saying SuperSymmetry algebra? Hold on, go back to that page for a moment. The second one. Not quite that one. Yes, sorry. This is the one. You can see some of that information here, but it's harder to identify. So things like supercharges, they are inherent in that notation, the SUMN notation, but that's harder to see here.
I'm seeing a lot of stuff about particle physics again. I'm not sure. So supersymmetric algebra is just a type of algebra related to particle physics. Why them keep on
Of
mentioning?
course. Can you go on Wikipedia, sorry, Google, and type supersymmetric group? Let's see what comes up, please. Supersymmetric group. Hold on. You can go on supersymmetry group in physics on Google and tell me what you find, please. Okay, I think I found something. I found. Okay, Matthew, I'm going to paste a link in the chat. Matthew, you there?
Yeah, I'm hearing you.
Here's
Oh,
a
it
link.
seems my mic was off. Yeah, what I think the question, I don't think you heard my question.
Look at that link. Oh, you're asking a question.
Yeah. So the
Posted the
question
link in the
was,
group pertaining to SUMN notation.
okay. So yeah, I think the question I was trying to ask is, I see, your train of thought where you're trying to find more or better weight spaces that lead to better representation of pause. So I see where you go from real numbers to convolutional real numbers to complex valued numbers to convolutional and complex valued numbers.
And those are all under the class
Yeah.
of symmetry groups.
Mm-hmm.
So one way to look at them is through that point of view, which is the usage of complex numbers and so on, and convolutions and those. And an additional way to look at them is from the perspective of symmetry groups. So with the usage of various symmetry groups, we saw representation for increasing. So for example, the SUMN thing I referred to, yet another one, is yet another symmetry group.
So you're saying your supersymmetric artificial nets use that group?
That's the goal here. That is
That's
the
a
goal,
goal.
to implement a model that would use SUMN based notation. So my notation now, if you go back to the paper there, if you go to my paper particularly, if you go to the top in the abstract, there's fine as well, the same place, sorry.
Here?
Same graph, if you go above.
Okay.
Yes, that theta x, phi x theta bar tw. Remember, I think I was explaining this to Matthew once, that all of machine learning, with the exception of my model, can be looked at as phi x theta tw. Joshua Benjo explained this in his book Deep Learning book, a famous book. I think I went through this with Matthew before, where we found the page on Deep Learning book, and we looked at, what page was it, Matthew? I think it was chapter 5.
I think it was chapter 5.
Manifold learning.
Let me see if I have.
And Benjo made a point that we can quantify machine learning like that. Did we pass it?
No, I'm not at chapter 5 yet.
Or is it 6?
I think it was
manifold learning somewhere, I think. I think I mentioned it on that Venn diagram that I had, the location of that notation. Hold on, Matthew, I think it's on the, is it there?
I think it's somewhere close to here.
Yes. Let us look on the diagram again. I think I pointed out the exact location, because I'm not remembering it now. Okay. It was 0.3 somewhere. On the top of the diagram, I think. Let's find the note what we chapter 6, page 166.3.
Oh, I see. Page 166. Chapter 6. Chapter 6. 666. Ah, yeah. Yeah. Here it is.
Yeah, so on point 3, all of machine deep learning, I should say, can be quantified in terms of this notation. We have phi there, a function which does transformations pertaining to some input space, x or input, phi or learned representation, which is just our weights when it's perturbed by our transformation, and some other operations representing a transformation and the affirmation weight. So phi theta there is our learned representation, and W there is our weights. So all of machine learning can be looked at from this scope. And my contribution now, my notation for supersymmetric ANNs, if you go to Yes, instead of the x theta tw there, we have x theta theta bar, that's a bar there. Tw is clearer when you look at the actual document. And Matthew, if we go to Wikipedia supermanifolds now, please. No, supermanifold. Yeah, so that's my notation there. But I want to go to Wikipedia supermanifold, not by me, but pre-established things. So if you go to Google now, I think you can click on supermanifold there, please. Yes, in physics, supermanifold, that's what the notation looks like. It's a very similar notation to, or very similar configuration to machine learning. X looks like some input space, and theta bar looks like some learned parameters. But in any case, my notation involves is built atop this standard supersymmetry based notation in physics, where we would perturb what would be supersymmetric weights, and we would learn supersymmetric parameters. Matthew, could we go back to the paper, please? My paper this time,
Okay.
so we can basically conclude now.
Yeah. Which part?
The same graph.
Oh, same graph. All right.
Yeah, so when we say normal space-time
Mm-hmm.
in physics, we're talking about things, for example, I'm not a physicist, but we know normal space-time is separate from fundamental physics. So right now, physicists are trying to find a way to unify classical physics
Mm-hmm.
and quantum mechanics because right now it's not rectified,
Yeah.
it's not unified, and supersymmetry is one possible solution for rectifying or for consolidating Einstein's special theory of relativity and quantum mechanics.
Quantum mechanics.
Supersymmetry is seen as one way to do that. So one thing to note is that it's not yet found at the Large Hadron Collider.
Yeah.
As in, no supersymmetric particles have been found because we know what supersymmetry. We're not physicists, but we know that supersymmetry concerns finding partner particles to some of the already discovered particles in the standard model.
Mm-hmm.
So although it's not yet found at LHC, we have seen that using formal methods from physics is benefited machine learning. So no longer are we talking about normal space-time, but we're looking at both normal space-time
Mm-hmm.
as seen in things from special theory of relativity, also as seen in things like SON-based groups, SUN-based groups, and also UN-based groups. But SUMN-based model, groups incorporate all the rest before it. So that would reasonably necessitate an increase in what we can represent. Remember now, the supersymmetric theory in physics, although we're not using that exactly, we're using things like the matrix configuration from the supersymmetric group, not using everything from physics. But on the point that these groups incorporate SUN, UN, and SON, we would expect to see some jump in representation for. After all, this is a theory that seeks to consolidate both special theory of relativity and also the fundamental theories. So since it's a theory that seeks to fight to consolidate these things, it must be able to incorporate all the features of the input space known as reality. So
I
not
see.
only of normal, yes?
Yeah, I'm getting a train of thought.
So not only we see what we see here that it incorporates prior groups and offers more operations, but the goal is really to try to use this model in that way. It's a very hard task,
Yeah.
Okay.
but that's all that goal is.
Yeah, I'm getting it too now. But I'm starting to think that what was the guy you spoke to again? He said you should worry about the implementation. I'm starting to worry that the reason this might not have been done already because it's exactly so hard to do something like implement this type of maths to create the functions you want. Yeah, that's really the important part to get to the implementation, because without that you can't really prove anything.
Yes, that is my ultimate goal.
Mhm.
Because once this is implemented, if I can manage to do it or find some help, it could be another, it's essentially a new form of deep learning
Mm-hmm.
field
Next
in deep
level.
learning. So all the prior things involve phi x theta tw, and this will involve something entirely different. Well, not entirely different, but just a new branch in deep learning.
Mm-hmm.
So it's a really hard and non-trivial task. So other,
So,
yes,
yeah. So I mean, do you have any do you have you set out like a path forward in terms of how you're gonna set out trying to implement this, in terms of maybe getting help from physicists or um experts with the math to try to see how, I mean, what's the best path forward in trying to implement something like this? Because I mean, I see where you have the general theory, of what you're trying to achieve, but that
hypothesis.
connection, that, yeah, exactly, the hypothesis, but that connection between the hypothesis and creating a real world, or not so much a real world experiment, but even proving it mathematically, or even creating an experiment that could show the effectiveness of your theory. That link there is, I guess, what you're trying to work on right now. Figuring that out.
Yes, I tried to contact some physicists. I don't,
Mm-hmm.
you know of Garrett Lacey. He's a
No.
physicist who,
Mm-hmm.
you know of him.
No, I don't know of that particular physics.
He worked on the E8 theory of physics, which is another God theory, a grand
Mm-hmm.
unification theory. He's a famous physicist. He lives in Havana, I think. He doesn't live anywhere, I think. And he likes to surf. But he's a popular physicist who is taken seriously by
Yeah.
the physics community. I spoke to him.
Mm-hmm.
He said it was a good idea. What was his exact word? It's documented somewhere in emails. I think I posted some of the email on the correspondence on the same Facebook AI group.
Yeah, I
I
think
put
you
the
had.
post here.
Yeah, I think you had sent us a chat
I put the
or
post here.
the email correspondence, the one where he was mentioning if you could try
No, I think
RL.
no, that email was between Ire Ospiral, which is a who is a
Oh,
PhD AI person.
oh, okay,
He
okay.
actually worked with Marvin Minsky, one of the fathers of AI.
Oh,
That was
nice.
between Ire and I. But this one now would be between Garrett Lisa, a physicist, not
Mm-hmm.
really an AI person, but I still sought his help for physics, knowledge, and guidance. But
Mm-hmm.
he expressed that is a reasonable idea to pursue,
Mm-hmm. Okay.
and that is promising because someone of that capacity mentioned that it's promising. So,
Yes.
but even without
Mm-hmm.
that advice, I still would want to pursue because it seems like a straightforward idea,
Yeah.
although hard to implement.
I see the
You can
logical.
see,
I definitely see the logical progression. With what you're trying to implement. Um, I mean, I think we can probably wrap up here.
yes,
Yeah, we definitely got. I mean, I personally got. First reading a theory, like I was, kind of what you say, more or less lost in terms of knowing exactly what exactly was the logical progression, but definitely after this chat that we had, I mean, I definitely understand more what your train of thought is.
Yeah.
yes,
So
it's
that, which is why I
Maybe
think things
change
like
it to
this
how you
is
do
is good.
it. Make it more.
What we're doing right now. Yeah,
and yes,
Dimitri, you're
it's
saying something?
Yes,
yes,
maybe can do some edits to the paper itself, make it
Mm-hmm.
more flow more logically in a direction that I want people to think about it. Like similar to how we go through it today.
Yeah, so actually a good suggestion.
of course,
Mm-hmm.
any type of help is or direction
Yeah.
is optimal.
All right. All right, guys. I guess this concludes a successful first meeting of our little association, or the beginnings, hopefully, of something special. Um, hopefully we can
Thanks a
see if
lot,
we,
guys, for the
yeah,
interest in this
thanks.
model.
Yeah, thanks to you for giving us the time to explain this. I can definitely say I found it very interesting, and learned some things here today. Yeah, hopefully this can be like a regular thing. I mean,
No problem. I try to use every word
mhm,
in a concise way in the paper.
yeah, yeah. So
So no
hopefully
word
from,
is okay.
yeah, I was just saying, hopefully from here we can continue doing discussions like this. Maybe on topics in AI, maybe we can pick papers that we see that are interesting, or even projects that we could
Any
think of
topic,
together.
any AI topic.
Yeah,
Yeah.
exactly. All right. So the Zoom meeting is about to run out. So I guess this is it. And next week, if anything, maybe I'll post a topic for next week in the WhatsApp, or we'll see. But yeah, thanks for coming,
Yes.
guys. All right. Bye.
Thanks a lot, Matthew and everyone.
Yeah, bye.
All right.